Hello everyone. In this work, we present a novel model that restores a complete facial images from partial observations from meetings in virtual reality. Visual contact is important for both real and virtual human social communications because it can increase the level of presence and comfort and promote close interaction among communicators. In this work, we focus on the visual contact problem in the context of VR meeting, where people might wear the VR headset and have an online meeting. We might expect something like this. However, what we have is actually like this. The VR headset blocks the real appearance and the visual contact is gone. We don't like this. We want to see the complete faces. The good news is that the VR headset usually has infrared cameras which is able to capture local facial regions in the dark environment inside the headset. So now the restoration problem becomes how can we generate the complete face from the partially captured local regions? Existing methods to this problem heavily rely on high-resolution person-specific 3D models which are prohibitively expensive to apply to large-scale scenarios. Our solution is to propose a 2D lightweight facial image composition network, which we call FIC-Net. To support our work and inspire more future works, we also built a new dataset to highly approximate the real use cases. The new data is used to train our 2D model. With the newly built dataset and the model design, we propose a novel stage-wise training schedule that carefully considers problem features. First, we introduce the dataset we have built. Our dataset is based on the MED dataset, where video clips of different persons are captured from 7 different perspective angles. We use a front view image at each frame as a ground truth, and use a complete face in another frame as a reference image, which is used to provide the facial context. The local patches that approximate the images by headset camera are cropped from different angled images with the same identity and same frame index as a ground truth. The raw composition of our data is like this. We analyze the data in terms of the homogeneity and heterogeneity. Our data is different from the data in conventional image editing tasks, where the images are usually homogeneous in terms of the geometry and color, meaning all pixels are captured from the same camera angle and all pixels are either RGB or grayscale. We call those types of image data homogeneous images. On the contrary, our data consists of images with different geometric views and color patterns, and we call those images heterogeneous images. There are different sources of the heterogeneities. It could be only geometry, it could be only color, and it could be both geometry and color. Our data is the same as the last one, which has the largest level of the heterogeneity. Our task is to convert the highly heterogeneous input images to homogeneous images. Based on our analysis, the key idea of this work is to decompose the large heterogeneities into smaller ones. According to this, we propose a simple but efficient local to global model structure. Here we show the framework of our model. For the local transformation module, we have 3 independent local models that transform local patches: the left eye, the right eye, and the mouth. The local models are trained using the MSE loss between the prediction and the ground truth. For the global fusion module, we aggregate the local predictions together and form a new global input with the context provided by the reference image. The global model is responsible for color prediction and further structure refinement. To enhance the quality of the global prediction, we use a domain discriminator as in-GAN to tell the real face or fake face. After having the data and the model, we propose a novel training scheme to maximize the model performance. We first split the training data into 2 sites, D1 and D2. In the first stage, we train local models only using the data in D1. In the second stage, we use local models trained in the first stage to predict frontalized patches for D2. Then, for each data sample in D2, we merge the predicted frontalized local patches and the context and generate a new set of data, D3. This D3 actually contains the images used for the global input. In the third stage, we use a newly generated D3 to train the global model. As we build the D3 based on D2, we can directly use the ground truth in D2 to supervise the training of the global model. In the last stage, we continue to train the local models using the data in D2 because the training of local models in the first stage never saves those data, and we should not ignore this part. We expect the final local models to be trained thoroughly using all of the training data. The reason of only using D1 in the first stage is that we need to generate data to train the global model in the third stage. We don't want the local models overfitting to all of the training data. In that case, the global model might be also overfitting to some good inputs. The existence of the stage 2 is to approximate the scenarios in the deployment and make sure that the input for the global model is consistent with the real use cases. Here we come to the results part. We have several baselines. FIC is our proposed model, AE is a simple autoencoder structure, PB is a Poisson blending, which is commonly used in many image composition tasks. SMG is a recent advanced Gaussian inversion-based image composition model. To establish a thorough evaluation setting, the evaluation data in our dataset has two tabs. One is a weak testing data, where the identities in the images are seen during training, but the expressions are not seen. Another one is a strong testing data, where neither identities nor expressions are seen during training. We compare different methods in both of the testing data. Here we show qualitative results. As we can see, our model achieves the best quality among all of the listed methods. A special thing about the Gaussian inversion-based method is that it can generate real faces, but in the weak testing data, the expected expressions are lost, and in the strong testing data, the expected identities are lost. The reason for this is Gaussian inversion-based method is trying to find the closest feature in the inversion space and decode it. There is no hard constraint to maintain the expression or identity. We also perform quantitative evaluations. Our model achieves the best results with fast inference speed. We have a series of application studies to validate the necessity of our design choices. We validate the usefulness of splitting the whole data into D1 and D2. It turns out that the splitting is necessary. We also compare the results with and without skip connections in our local models and global model. The results show that removing the skip connection is a good move because we're dealing with heterogeneous images. Lastly, we further show the insufficiency of Gaussian inversion-based methods using FFHQ images. As we can see here, the model shows the same problem as in our dataset. The identities are lost. Thank you.